Okay, morning everybody. We're going to carry on today with our partial fractions, and today we're going to look at what we need to do when we have an improper fraction. I very briefly covered what an improper fraction was yesterday. Let's do that properly today. So just a couple of definitions first, just in case we've forgotten certain things. So one thing we need to remember is a polynomial is something of the form the word something was right to use that, but never mind. Something of the form an xn plus an minus 1 xn minus 1 plus an minus 2 xn minus 2 plus dot 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 all the way down to a0 x to the 0. In other words, a polynomial is something which has x terms with some power, and that x term has a coefficient in front. An is the coefficient of the xn term. The most common polynomial you guys have come across is quadratics. Quadratic is one where you'd have the x0 term, the x1 term, the x squared term. So in that case, n would actually just be 2. You've also come across cubics. You've probably come across quartics every now and again, but we don't really focus on those very much. So that's all a polynomial is. If you've got a polynomial like this one in particular, we would either say the order is n, so it's a polynomial of order n, which just means what's the highest exponent out of all the terms, and we say that this term at the front here is called the leading term. So this is the leading term because it's got the highest order exponent in it. So, for example, if I had some polynomial function, let's go for 6x cubed plus 2x squared plus x plus 17. Just have a quick think to yourself now, what would the leading term be, and what's the order of this polynomial? Okay, so the leading term is this one. This is a term, this is a term, this is a term, and this is a term. This is the leading term, not because it's at the front, but because it's got the highest exponent on its x term. So the leading term would be 6x cubed, and the order of this polynomial is whatever the exponent is of the leading term. So this would be of order 3. There's also another word for describing the order. Oh, hello, Maximilian. Are you coming in?
No, Mama said no.
Bye-bye. Hang on, let me just pause this video. So if we turn this round and then we flip it up, we might be able to set that with the right way around. There we go. Oh, say hello, everybody.
Hello, everybody.
Oh, you probably can't. The microphone's here. Do you want to say hello into this bit?
Hello.
Do you want to tell everyone about numbers?
Numbers.
What's your favourite number? You like number 8 because he's an octonaut. No. Octablock. Octablock! Right, bye-bye. You can watch me later, yeah. Okay, that's disappeared now. So leading term, 6x cubed, order was 3. Okay, so now let's get on to what an improper fraction is. So, or an improper algebraic fraction anyway. An improper algebraic fraction is one where the order of the numerator is greater than or equal to the order of the denominator, to the order of the denominator. So for example, if I had 6x cubed plus 2x plus 4 all over x plus 1, x plus 2, x plus 3, this would be an improper fraction. And the reason for that is if you expand this out on the bottom, you would get an x cubed term. The order of the numerator is 3, the order of the denominator is 3, and if the numerator is equal to the order of the denominator, it's improper. If I change this to a 4, it would still be improper. If I change this exponent to a 2, it would then become a proper fraction. We're going to deal with improper fractions today because they need a little bit more, they need us to be a bit more delicate when we try to split them up into partial fractions. Okay, just change this slightly so I can write still. Okay, so we're going to crack straight on with an example now, and it's quite a cumbersome example. Let me just sketch it. Okay, so let's start with a fraction. So our fraction is 4x cubed plus 10x plus 4 over x 2x plus 1. So hopefully you can see straight away that this is an improper fraction because if I expand the bottom out I get a quadratic, there's a cubic in the top, and the order of the top is bigger than the order of the bottom. So before basically the issue is that I need to have the numerator to have an order less than the denominator. If I can do that, if I can cheat somehow, then I can just carry on with the methods we've already learnt in the last 3 lessons. So what I'm going to do is I'm going to just write this out in expanded form. So I'm going to expand the denominator out to get 2x squared plus x. And then what I'm going to do is I'm going to use a fact we had yesterday. Something we did yesterday was this. Dividend over divisor, in other words the fraction, is equal to quotient plus remainder over divisor. So we're going to start doing long division, but we're not necessarily going to have to go all the way down to the end. We could stop halfway and call that the remainder instead. And as long as we stop at a point where we've got a remainder which has got order less than the divisor, then we can say whatever our fraction is equal to the quotient that we had so far plus what fraction we've got left over. Okay, let's just do that for example here because that's going to help us. Okay, so let's do some long division. Oops, daisy. 2x squared plus x into 4x cubed plus 10x plus 4. Okay, so 2x squared into 4x cubed. What do I have to times this by to get that? I'll have to times this by 2x. Right, before I carry on, I've realised that I've made a slight mess up. So just this is something for you all to be aware of. At the moment, my dividend has got an x cubed term, it's got an x to the 1 term, but it hasn't got an x squared term. So what I'm going to do is I'm actually going to start again, but I'm just going to make a slight adjustment because that's going to cause me an issue in a moment if I don't deal with the fact that there's no x squared term. So I've got 4x cubed plus 0x squared plus 10x plus 4. You'll see in a second why I've done this. So 2x squared and 4x cubed, I'd need to times this by 2x to get that. Where do I put the 2x? I have to put it above here. So my x's line up in the right place. Second step, 2x times this gives me 4x cubed. 2x times x gives me 2x squared. And this is the reason why I put that 0x squared in, because I knew this was going to happen. If I take those away from each other, I've got 0, take away 2x squared, which gives me negative 2x squared. And I'm going to bring down my 10x. And at that point, I'm going to stop and say to myself, I've done one full round. So when I bring down, that's when I've done a full round. What have I got here? What have I got here? I know from what we did yesterday that remainder over divisor is what I'm interested in. This is my current remainder. My divisor always stays the same. And at the moment, my remainder and my divisor are order 2 polynomials. So I need to keep going because I really need a remainder which has got an order slightly less than the divisor. So let's do another round. 2x squared into minus 2x squared is minus 1. Minus 1 times this gives me minus 2x squared minus x. And if I take one away from the other, 10x, oh, they kill each other, 10x take away negative x gives me 11x. And I bring down my plus 4. And at this stage I could probably go again, however, there could be some confusion actually here what we'll do next, but let's just gloss over that for a sec. Now I've got a remainder here, and my remainder is definitely less in order than my divisor. So what I can say is I can use what I did yesterday, this idea, dividend over divisor, etc. So I can say dividend over divisor equals quotient plus remainder over divisor. This is my dividend over divisor there. Let's just put this up a bit so we can see more stuff. This is my dividend over divisor. So I've got 4x cubed plus 10x plus 4 all over x 2x plus 1. I've stuck this back into its factorised form because I know when I'm doing partial fractions that that's the easier way to have it. The quotients here is 2x minus 1. And then I need to add the remainder. The remainder is 11x plus 4 over the divisor. The divisor is 2x squared plus x. Okay, so that's my setup at the moment. I've got this, and it's going to be, well, somewhat in partial fractions. We've got 2x, we've got minus 1, and then we've got this stuff here. So let's find out what 11x plus 4 over 2x squared plus x is. Okay, so, no, I've been right silly sausages there, haven't I? It should be x over 2x plus 1. It should be x, 2x plus 1. So we've got a over the first linear factor. The first linear factor is x plus b over the second linear factor. The second linear factor is 2x plus 1. And so if I times through by the denominator, I'm going to get 11x plus 4 is equal to a lots of 2x plus 1 plus b lots of x. So I've got a couple of choices here. I can go for x is 0. If x is 0, I've got 11 times 0 plus 4 is equal to a 2 times 0 plus 1 plus b lots of 0, which gives me 4 is equal to a. Similarly, I want to try and find b now. I'm going to kill this one here, and I'm going to kill that by making x to be minus a half. So x is equal to minus a half. I've got 11 times minus a half, I hope it was that anyway, plus 4. Just double check that, plus 4 equals a 2 times minus a half plus 1 plus b lots of minus a half. And so what I can do here is just tidy this up a bit. I've got minus 11 over 2 plus 4 is equal to, that dies, this is minus b over 2. If I times both sides by 2 to try and get rid of these 2's, I need to times every term by 2. That becomes minus 11 plus 8 is equal to minus b. And minus 11 plus 8 is minus 3. Minus 3 equals minus b, so b must be 3. And therefore the punchline, he says, having to look back some pages, 4x cubed plus 10x plus 4 all over x 2x plus 1 is equal to, what was it, 2x minus 1 plus 4 over x plus 3 over 2x plus 1. Oof. Right, so that was rather a long process, but individually you guys and can do all those things separately, and that's what we've been doing all week. So this division is what we did yesterday. We focused on this fact yesterday a bit as well. We did this extensively on the first 2 lessons, and so basically all we're doing today is saying, okay, all of those things together, can we do this for an improper fraction? And of course we can. So can you guys, for the last lesson we have on partial fractions, can you do exercise 1G? And I will speak to you again on Monday, and we'll be looking at the binomial expansion. Have a lovely few days in your house, and I'll speak again soon. Bye-bye.